In this video, you will learn how to obtain the formula when you are given the name of a binary compound. It is a continuation of a previous one called Science Easyfied, Chemical Nomenclature of Binary Compounds, which also covers this topic and has many worked out practice problems. Recall that there are two groups of binary compounds: those composed of two nonmetal elements which are covalently bonded, and those composed of a metal element and a nonmetal element which are ionically bonded. Once you determine the category to which the binary compound belongs, you can start constructing its formula or its name in accordance with its specific rules. Note that in this video, I will be deliberately avoiding the terms ionic and covalent, as I don't find their use necessary in this presentation. Science is often considered a very difficult subject, mainly because there is so much material to memorize. But a way around that is to use mnemonics. A mnemonic is a memory device, such as a sentence or an acronym, that helps you remember something. Two mnemonic jingles will help you remember the rules for binary nomenclature: non-metal, non-metal Greek, and metal, non-metal, non-Greek. Note the two nons in each jingle, and you've memorized the rules. The use of Greek number prefixes in the non-metal, non-metal group means that the name spells out the formula, and the formula spells out the name. Easy enough. But because of the absence of Greek prefixes in the metal-non-metal group, the name does not spell out the formula, and therefore, to figure out the formula requires a more complicated process. Let's go over an example of a non-metal compound to appreciate the close connection between the name and the formula. Examining the name disilicon hexabromide, you would immediately know that it's a non-metal compound because of the Greek prefixes. The formula Si2Br6 is right there, spelled out by the name: 2 silicon atoms and 6 bromine atoms. However, there is an important difference between the name and the formula, and that is in the way the items are ordered. In the name, the number comes before the element. And in the formula, the element, written as a symbol, comes before the number, written as a subscript. What if you had to do the reverse? In other words, what if you are given the formula and you need to provide the name? First, you classify the elements. The symbol Si stands for silicon, and silicon is a nonmetal. Br stands for bromine, and bromine is also a nonmetal. So the non-metal rule applies. The formula spells out the name, and you will use Greek prefixes to express the number of atoms: 2 silicons and 6 bromines. The name is disilicon hexabromide. Easy enough, isn't it? But only if you know your rules and your Greek prefixes. If you need a review of the rules for naming non-metal compounds, watch my previous video, Science Easyfied, Chemical Nomenclature of Binary Compounds. And if you need a review of the Greek prefixes you are most likely to encounter, memorize the following. But if you're comfortable with the rules and would like to practice, you can quiz yourself with the next 3 compounds. I will give you a name, you provide its formula. At these visual prompts, pause the video, think about the answer, Then click to resume the video and to check your answer. Question 1. What is the formula for dinitrogen monoxide? Answer: N2O. Question 2. What is the formula for carbon tetrafluoride? Answer: CF4. Question 3. What is the formula for trisulfur pentachloride? Answer: S3Cl5. Metal-nonmetal compounds are more complicated. Check out the names of these three compounds. Because there are no Greek prefixes to spell out the formula, you need to use another technique to figure it out. And to be able to do that, it's a good idea to start with a review of atomic structure. An atom is made up of a nucleus that houses the positively charged protons, which in representations are expressed as P+, and the neutral neutrons expressed as N0 or N0. Negatively charged electrons, expressed as E-, reside in the space surrounding the nucleus and move around the nucleus in fixed regions of quantized energy. A model referred to as the Bohr model shows these regions as circular and compares them to the planet's orbits around the Sun. However, it is important to keep in mind that this model is simplified, but because it still provides valid explanation for basic concepts, it is widely used in elementary chemistry. The regions inhabited by the moving electrons are called orbits, shells, or energy levels. These are numbered starting with the one closest to the nucleus, and they match the periods or rows on the periodic table. For example, hydrogen in period 1 has 1 energy level. Calcium in period 4 has 4 energy levels, and so on. A slightly more advanced model shows the electrons paired up as they actually are in an atom. But a condensed, simpler drawing of the model is more commonly used. This shows a nucleus with the number of protons and partial shells with the number of electrons at each level. In some situations, this simplified model may also show the number of neutrons in the nucleus. The last shell, or the outermost energy level, is called the valence shell, and the electrons located there are called the valence electrons. Energy levels, designated by the letter N, can hold a fixed maximum number of electrons. The first energy level, where N is equal to 1, can hold a maximum of 2 electrons. The second energy level, or N is equal to 2, can hold a maximum of 8. The third energy level can hold a maximum of 18. The fourth, a maximum of 32, and so on. Like so much about the behavior and properties of atoms, this number follows a pattern. We will tabulate the information we just learned in order to understand it better. Then, after close examination and some time for puzzle solving, we notice that a mathematical relationship emerges. The maximum number of electrons in energy level N is equal to 2 times the energy level squared. Let's confirm the calculations. And how about the other energy levels? What is the maximum number of electrons in n equals 5, n equals 6, and n equals 7? Our calculation shows that energy level 5 can hold a maximum of 50 electrons. Energy level 6 can hold a maximum of 72, and energy level 7 can hold a maximum of 98. And indeed, these numbers are confirmed by the electron configuration of the elements at these levels. But here is a point of great importance. The chemical stability or reactivity of an atom is determined by its valence shell, which may not necessarily hold the maximum number of electrons. Energy level 1 becomes chemically stable when it contains 2 electrons. Energy level 2 is chemically stable when it holds 8 electrons. At these two levels, the valence shell is stable only when it holds its maximum number of electrons. But at all subsequent energy levels, the valence shell is stable with 8 electrons. For this reason, the number 8 is considered a magic number in chemistry, and in this context, we call it the Octet Rule. Simply stated, the Octet Rule refers to the tendency of atoms to achieve chemical stability with 8 electrons in the valence shell. Because the first energy level is an exception, the principle is often referred to as the 2888 rule, which, in my opinion, is a better name. Let's tabulate this information. When an atom has an unstable valence shell, it will tend to react with another atom in order to satisfy the 2888 rule. It will do so by losing, gaining, or sharing its outermost electrons so that all atoms end up with a stable valence shell. With this information under our belts, we can go back to chemical nomenclature. We'll look at the reaction between a sodium atom and a chlorine atom, figure out the name of the compound formed as a result of a chemical reaction between them, and go through the steps to figure out how they combine in order to get the formula of the compound. Before anything else, we can give the name of the compound. Knowing that sodium is a metal and chlorine is a nonmetal, we determine there will be no Greek prefixes. The name is straightforward: sodium chloride. But the formula is more complicated. Because of the absence of number prefixes, the name does not give us any clues about how many atoms are involved in the reaction. This is where the 2888 rule can help us set up the steps for getting the formula. Start out by drawing the simplified atomic model for both elements. As a group 1 element, sodium has 1 valence electron, and as a group 7 element, chlorine has 7 valence electrons. During a reaction between a metal and a nonmetal, an exchange of electrons takes place where the end result is an outermost stable shell for both atoms. This is called octet stability. To achieve octet stability, in other words, to achieve a stable valence shell of 8 electrons, sodium can gain 7 electrons or lose 1. The tendency is to lose 1 because losing 1 involves less energy. To achieve octet stability, chlorine's tendency is to gain 1 electron because less energy is required to gain 1 than to lose 7. Here is how the reaction works. Sodium loses its single electron to chlorine, and its third shell now has 0 electrons. Note that a shell is not something concrete. It is simply the space that electrons occupy during their orbital movement around the nucleus. So, having lost its electrons, sodium's third shell no longer exists. Its second shell becomes the outermost shell, and with 8 electrons, it is stable. Chlorine, having picked up sodium's electron, now has 8 valence electrons, making its third shell stable. Thus, the exchange has created stable valence shells for both elements. We say that the elements have bonded, forming a binary compound composed of a 1-to-1 ratio of sodium to chlorine. To express the formula, we write the symbol of the metal, followed by a subscript that denotes the number of atoms, then the symbol of the nonmetal, also followed by a subscript of the number of atoms. Recall that we never write subscripts of 1, so the formula for the compound resulting from a chemical reaction between sodium and chlorine is NaCl, and the name is sodium chloride. Let's go through the same steps for magnesium and chlorine. Magnesium is a metal, and chlorine is a nonmetal. Following the metal-nonmetal non-Greek rule, we determine that the name of the compound formed from the reaction of these two elements is magnesium chloride. Now we work out the formula. We draw the simplified atomic model for both elements. Magnesium in group 2 has 2 valence electrons, and chlorine in group 7 has 7 valence electrons. To gain stability, the valence shell of magnesium will lose 2 electrons, and the valence shell of chlorine will gain 1. Once chlorine has gained 1 electron, its valence shell becomes stable. But magnesium, with 1 remaining electron in its valence shell, is still not stable. Another jingle will help us determine what will happen next. The unstable one will seek another. Magnesium, still unstable, will seek out another chlorine atom which will accept its last valence electron. Now, the second chlorine atom has 8 electrons in its valence shell and is stable. With no electrons, magnesium's third shell disappears and the second shell becomes the valence shell. Thus, through a loss and gain of electrons, all 3 atoms have stable valence shells satisfying the octet rule. Bonding has taken place, and the formula for the compound that results from this reaction is MgCl2. And the name is magnesium chloride. And as a last example, we'll work on the reaction between magnesium and phosphorus. Once you classify magnesium as a metal and phosphorus as a nonmetal, you determine that there will be no Greek prefixes in the name of the compound formed as a result of their combination. Magnesium plus phosphorus yields magnesium phosphide. Let's figure out the formula. Here are the simplified atomic models for the 2 elements. Magnesium has 2 valence electrons to give away, and phosphorus, with 5 valence electrons, has room to pick up 3. Follow the animations, paying attention to the valence shells to see what happens as magnesium and phosphorus react with each other. After giving its 2 valence electrons to phosphorus, magnesium's outermost shell disappears and the second shell becomes the valence shell. With 8 electrons, this shell is complete and stable. However, phosphorus, short of 1 electron in its valence shell, is not stable. Our jingle reminds us what will happen next. The unstable one will seek another. Phosphorus seeks out another magnesium atom to fulfill its octet. It will pick up one electron from magnesium and become stable. Now, magnesium is not stable. The unstable one will seek another. Magnesium will seek out another phosphorus atom to which it can give its one remaining valence electron. Magnesium is now stable, but this second phosphorus is not. The unstable one will seek another. Phosphorus will seek out another magnesium atom. Magnesium's two valence electrons are just enough to completely fill the two empty spaces in phosphorus's valence shell. Phosphorus is now stable, and so is magnesium. With all players stable, we can now construct our formula, which represents a ratio of 3 magnesium to 2 phosphorus, Mg3p2. And the name is magnesium phosphide.
I have a question. A question here.
Yes, Joey, what is your question?
Do I have to do this every time I want the formula of a metal-nonmetal compound?
The answer is no. There is an easier way called the Octet Rule. And to understand how this easier method works, it is important to review what happens to an atom's valence electrons during a chemical reaction. We've already seen a little of that in the 3 reactions we've examined. We noted that sodium tends to lose 1 electron. Magnesium tends to lose 2 electrons. Chlorine tends to gain 1 electron. And phosphorus tends to gain 3 electrons. How about the other elements? Let's talk about the groups one by one. At this level of chemistry, we will focus on the main group elements. One system of identifying the groups uses Arabic numbers 1 to 18. Another system uses Roman numerals 1 to 8. However, note that if we eliminate the digit 1 in groups 13 to 18, we end up with the same numbers in both the Arabic and the Roman systems. I prefer the Roman system because it is more indicative of the number of valence electrons. Now, let's add a visual of the valence shell for the elements in these 8 groups. Note that group 8 is somewhat of a mislabel. As mentioned before, the Roman numeral system indicates the number of valence electrons, but in this last group there is one exception. Helium with only 1 shell has 2 valence electrons. Nevertheless, the group is referred to as group 8. An atom in group 1 has 1 valence electron. It can gain stability by losing its 1 electron to another atom or by gaining 7. The tendency is to lose 1 because less energy is involved. An atom in group 2 has 2 valence electrons. By the same logic, it can gain stability by losing 2 or by gaining 6. The tendency is to lose 2 because losing 2 requires less energy. Group 3 follows the same concept. It is easier to lose 3 than to gain 5. The argument for group 4 is straightforward. Losing 4 electrons is as easy as gaining 4. Now, let's see how, by the same logic, groups 5, 6, and 7 are more inclined to gain electrons than to lose them. It is easier for group 5 elements to gain 3 than to lose 5. It is easier for group 6 elements to gain 2 than to lose 6. It is easier for group 7 elements to gain 1 than to lose 7. In group 8, the valence shell is stable. Whether an atom has one valence shell with 2 electrons, as is the case with helium, or whether it has 8 valence electrons, as is the case with the other group 8 elements, an atom in this group is stable. The tendency is not to react. There is no loss or gain of electrons. Scientists tabulate results in order to have them all in one place. Tables and charts make it easier to analyze the data, to detect patterns, and to reach conclusions. Let's tabulate the observations we have just made. After placing all our data in one chart, we notice that elements in groups 1, 2, and 3 have a tendency to lose electrons, and elements in groups 5, 6, and 7 have a tendency to gain electrons. We can conclude that in general, in a reaction between a metal and a nonmetal, metals lose electrons and nonmetals gain electrons. Metals in group 1 will lose their 1 valence electron. Metals in group 2 will lose their 2 valence electrons. Metals in group 3 will lose their 3 valence electrons. And in group 4, either the 4 valence electrons will be lost or 4 electrons will be gained. Nonmetals in group 5 have 5 valence electrons. To complete their valence shell, they will gain 3 electrons. Note that the number 3 is obtained from the octet 8 minus the group number 5. Nonmetals in group 6 have 6 valence electrons. They will gain 2 electrons obtained from 8 minus the group number 6. Nonmetals in group 7 have 7 valence electrons. They will gain 1 electron obtained from 8 minus the group number 7. With their shells already stable, group 8 elements will neither lose nor gain electrons, and there is a zero exchange of electrons, 8 minus the group number 8. For the most part, they are unreactive or inert. So reactivity is all about stability of the valence shell, and when atoms react, they essentially acquire the electron configuration of an inert group 8 element. For the purposes of this lesson, what's important to take away is not so much whether electrons are lost or gained, but the number of electrons that are involved in an exchange. These numbers are 1, 2, 3, 4, 3, 2, 1, 0, corresponding to groups 1 to 8 respectively. We'll take these numbers and place them in their correct positions on our periodic table. And then use them in a quick technique to find the formulas for the compounds that result from a chemical reaction between a metal and a nonmetal. This quick technique is called the crossover method or the crossover rule. To see how it works, we'll go back and use it for the 3 compounds whose formulas we figured out the long way. We'll start with the first example, sodium chloride, and ask the question, what is the formula for the compound formed from a chemical reaction between sodium and chlorine? Using the periodic table, we find the location of the elements. Sodium is in group 1. Its symbol is Na. Chlorine is in group 7. Its symbol is Cl. Sodium's location to the left of the zigzag line indicates that it is a metal. And chlorine's location to the right of the zigzag line indicates it is a nonmetal. Therefore, the metal-nonmetal rules apply, and both in the name and in the formula, the metal comes first. We confirm that the symbols are written in the correct order. Also, keep in mind that the crossover rule is only used for figuring out the formula for metal-nonmetal compounds. We don't need to use this technique with nonmetal compounds because there, the formula is basically spelled out by the Greek prefixes in the name. We now focus on the number of valence electrons that these elements would tend to lose or gain. Remember, these numbers are 1, 2, 3, 4, 3, 2, 1, 0, respectively for groups 1 to 8. When you use the crossover rule, it is not necessary to be concerned about whether there is a gain or loss of electrons. All you need to note is the number involved. To the right of the symbol of each element, as a superscript, we will write the number that corresponds to that group. For sodium, Na, which is a group 1 element, we write 1 as a superscript. For chlorine, Cl, which is a group 7 element, we also write 1 as a superscript. Remember that for group 7, the number 1 is obtained from 8 minus the group number. Now it is time to cross over. Elements exchange superscripts, which now become their subscripts. Finally, we remove the numbers 1. The formula is NaCl, just like what we had obtained using the long way with the diagrams of the simplified atomic models. And the name is sodium chloride. We'll follow the same procedure to answer the question, what is the formula for the compound formed from a chemical reaction between magnesium and chlorine? On our periodic table, we'll make note of the number of valence electrons lost or gained. Remember, these numbers are 1, 2, 3, 4, 3, 2, 1, 0. We find the location of the elements. Magnesium is in group 2. Its symbol is Mg. Chlorine is in group 7. Its symbol is Cl. Magnesium, located on the left of the zigzag line, is a metal. Chlorine, located to the right of the zigzag line, is a nonmetal. We confirm that the symbols are written in the correct order with the metal first. As superscripts, we will write down the numbers of electrons lost or gained. That's 2 for magnesium and 1 for chlorine. Remember that this number 1 is obtained from 8 minus the group number 7. Cross these numbers over and write them as subscripts. We remove the number 1. The formula is MgCl2. And that's what we got when we did it the long way. The name is magnesium chloride. And the last example. What is the formula for the compound formed from a chemical reaction between magnesium and phosphorus? Set up the periodic table. Magnesium is in group 2. Its symbol is Mg. Phosphorus is in group 5. Its symbol is P. Confirm that the metal comes first. The number 2 is placed as a superscript for Mg, and the number 3, obtained from 8 minus the group number 5, is placed as a superscript for P. Cross over the two superscripts. We see that the formula is Mg3P2, the same as what we had obtained doing it the long way. And the name is magnesium phosphide. Now it's time for you to try a few examples. I will give 4 problems and you will have a chance to work them out. At the prompts, pause the video, think about the answer, then click to resume the video and to check your answer. It's best to practice using pencil and paper. Are you ready?
I'm so ready.
Problem 1 has 3 parts. Part A. Use diagrams of simplified atomic models to determine the formula for the product formed from a chemical reaction between magnesium and oxygen. Now confirm your reasoning and check your answer. You started out by drawing the simplified atomic model for both elements. Magnesium in group 2 is shown with 2 valence electrons, and oxygen in group 6 is shown with 6 valence electrons. To gain stability, the valence shell of magnesium will lose 2 electrons, and the valence shell of oxygen will gain 2. With this exchange, the valence shells of both elements have become stable. The drawings represent a ratio of 1 magnesium atom to 1 oxygen atom. And the formula is MgO. Part B. Give the name for this product. The name is magnesium oxide. Part C. Use the crossover rule to determine the formula for the product formed as a result of a chemical reaction between magnesium and oxygen. Are you ready to check your answer? Using the periodic table, we find the location of the elements. Magnesium is in group 2. Its symbol is Mg. Oxygen is in group 6. Its symbol is O. Magnesium's location to the left of the zigzag line indicates that it is a metal, and oxygen's location to the right of the zigzag line indicates it is a nonmetal. We ensure that the symbols are written in the correct order with the metal first. We now focus on the number of valence electrons that these elements would tend to lose or gain and write those numbers as superscripts to the right of their corresponding symbols. For Mg, we write 2 as a superscript. For O, we also write 2 as a superscript. Remember that for group 6, the number 2 is obtained from 8 minus the group number 6. Now it is time to cross over. We remind ourselves that the subscripts 2 and 2 are ratios that need to be reduced to 1 to 1. Finally, we remove the numbers 1. The formula is MgO, just like what we had obtained in Part A using the long way with the diagrams of the simplified atomic models. The last 3 problems have 2 parts each. Problem 2, Part A. Use the crossover rule to determine the formula for the product formed as a result of a chemical reaction between sodium and oxygen. Answer: the formula is Na2O. Part B. Give the name for this product. Answer: the name is sodium oxide. Problem 3, Part A. Use the crossover rule to determine the formula for the product formed as a result of a chemical reaction between lithium and phosphorus. Answer: the formula is Li3P. Part B. Give the name for this product. Answer: the name is lithium phosphide. Problem 4, Part A. Use the crossover rule to determine the formula for the product formed as a result of a chemical reaction between aluminum and nitrogen. Answer: the formula is ALN. Part B. Give the name for this product. Answer: the name is aluminum nitride. Answer: The formula is ALN. Part B. Give the name for this product. Answer. The name is aluminum nitride. This completes the two-part series on binary nomenclature. Thank you for watching. I hope this video was helpful.